it's not, yeah, it's not that difficult. So, anyone has heard of the Rollup before? Okay. Zero knowledge proof, modular blockchain. Okay. Okay. Um, so I will start with my brief introduction of myself. I'm founder of Radius. Radius is building trustless shared sequencing layer for rollups. This words might kind of difficult for you, but I will explain what this sequencing thing is, why is trustless, why is it shared, and rollup. So, and also actually I worked previously I worked for Samsung Research as a software engineer for more than 13 years. I worked there for security and privacy research. At the time, I thought that privacy tech was really needed for blockchain to be mainstream of IT infrastructure. So that's when I founded zero knowledge research community called zk-soul in 2019. So it's all. So what zk-soul does is that we usually take a sponsorship from zk-based projects such as Starkware, Polygon, Anoma Elio, and then we do a deep technical research into that project and then host monthly based meetups. So right now there are more than 800 community members at this moment. So if you are really interested in learning ZK or like doing some toy projects with ZK, please join this community. And then I did a couple of grants program from Ethereum Foundation and Tejos Foundation. Especially from Ethereum Foundation, I did MEV resistance AMM. Have you heard of MEV? No, yeah. So MEV. So I will talk about this MEV. Why is it controversial? Why is it really important for rollups in the perspective of the rollups, especially just sustainability as well. So, and then Tejos, I kind of researched stateless layer 2 project. So basically, I'm kind of a describe myself as a technical guy, not like a economic or NFT DAO stuff. So before getting started, I will start with this. What's blockchain to me? Actually, I started kind of blockchain career since 2016 in Samsung. I started in-house study group called something like a blockchain. We just started the technical aspect of blockchain, not economic one. So it's a shame that I didn't buy any Bitcoin at the time. But since 2016, I've witnessed everything. I mean, I saw that my assets was doubled when I was asleep all night. Market collapsed, and then I also saw that some kind of discussion about what's the proper block size for Bitcoin, like 1 megabyte is okay or 2 megabyte okay. This discussion sounds kind of silly, but at the time it was really serious. So, and then I think that blockchain is kind of a red pill. Have you? I mean, actually, I put this one, the movie called Matrix, but I just find out that this movie came out in 1999. So some of you guys are not born. So, but you know what I mean. If you take a red pill, you are willing to learn some life-changing techniques, life-changing things. But I don't think that blockchain is kind of a change everything in your world. I mean, it's kind of I sometimes describe blockchain like a religion. So if you believe the concept of the world that blockchain wants to be built, you can take it, or you can just stay here, believe in government or centralize the system, but you can like enjoy this kind of efficiency that this kind of a centralization system give you. So it's your choice. Not like everything should be based on blockchain, but there are some aspects that it kind of fun. So okay, so okay. I know. So anyway, I will keep going. And then it was really kind of breakthrough to me that you can design some kind of architecture with this some concept of economics. So economic thing is really kind of breakthrough that blockchain gave us. So economic thing, and then yeah, as I said before, I don't think that blockchain is going to change everything. So it's really, really exciting experiment, I would say that. So I think you should be kind of proud of yourself that to be here to like to witness with your eyes that probably some the world that is going to be changed with the blockchain. So it I would say that it's experiment. So because it's might fail, might succeed. So I hope it succeeds. So anyway. So today's lesson is object that I'm gonna explain that the principles of sorry about that. Scalability solution in blockchain, especially why I chose Rollup-centric Ethereum as just the title of this seminar is that Ethereum is one of the projects that are really like putting so much effort to build a scalability solution, especially. So there was state channel, plasma concepts, and rollup. I think you should it might be helpful for you to understand how this scalability solution has been so far. So why rollup is kind of that scalability solution that Ethereum Foundation finally chose to as their ultimate scalability solution. And then another one is that you can understand how this Ethereum will go with this rollup. So as I said before, modular blockchain is at this time really getting really hype. So you can achieve effective scalability if you take some kind of modular concept. So I will start. So okay. So I think you are familiar with the scalability, but I'd like to define scalability more clear. To indicate that how effectively blockchain can process an increasing volume of transactions. So high scalability means that if these transactions and the number of transactions and user increase, the blockchain can maintain or improve its performance. If it's low scalability, it cannot. So actually, it's this vertical scaling, horizontal scaling. It's kind of terms that from a traditional database system, but it also applies to this blockchain system as well. So vertical scaling means that you can handle this increased transactions with the increased size of instance, for example, RAM, CPU performance in one single instance. So another one is that horizontal scaling, that you can add, for instance, to increased number of transactions. So there are some projects, some blockchain projects that take some kind of a vertical scaling, especially like Solana, for example. Solana requires these computing resources really high, so they can process more than, suppose, 10,000 transactions per second. But this horizontal scaling thing is that probably Ethereum or other blockchain projects help like this. So there are scalability limitation at this moment because Ethereum is kind of famous or notorious for having lower scalability. It just process only 15 or at most 45 transactions per second. But when every time Ethereum is criticized with this lower scalability, they said that it's designed for that. So you will see what you mean in the next slide. But there are limited resources like a CPU is limited. The storage space is also limited because you can put only like for example, for Bitcoin, you can only put at most 1 megabytes or at most 2 megabytes for each block. So also bandwidth is limited. So you can see, you can think of blockchain kind of with limited resources computing system. So compared to Ethereum, Visa, or any traditional centralized system, handle a lot of transactions per second. So, okay. There was some scalability, but as I said before, Ethereum is kind of designed for that because you might have heard of this blockchain trilemma, that there are scalability, security, decentralization, that every system can have only two features out of these three. So blockchain is kind of only take this security and decentralization system. So yeah, it's really difficult to maximize these all three items simultaneously in one blockchain. So current Ethereum is high security, high decentralization, and low scalability. But layer one is the kind of this high security and decentralization and low scalability, but they are trying to fulfill this other scalability while remaining this high security and decentralization. So they really trying to hard to do that. So you will see a couple of things that Ethereum Foundation has been trying to maximize scalability. So first one is sharding. Have you maybe out of it, but we say that sharding is kind of on-chain scaling because every computation happens in Ethereum virtual machine. So on-chain means that we need to modify Ethereum client software itself. So sharding is kind of also from this traditional database system, but it's kind of process of partitioning database. So if there is like for example 100 user base, like A, B, C, D, each sharding take care of these 25 people's transitions. So individual sharding is responsible for processing, verifying those kind of things. But the problem is that it's okay to process transactions if these transactions happens between two people who belongs to this like A shard, but the problem happens when one A to one B transactions happens. So this cross shard thing was really difficult. So that's why they kind of gave up this sharding solution. But you can see later that there is some proposal called bank sharding. This sharding system was proposed to process transactions and then also store the transaction data related to these transactions. But the transactions happens between for across shards. So bank shards proposal is kind of they only sharding for data storage. So you will see what kind of problem bank sharding is solving with support from the Rollup architecture. So off-chain scaling thing, there are a couple of things. As I said, it's before state channel, plasma, Rollup. Rollup is also there is optimistic Rollup, zk-rollup, and other inside chain. Off-chain means that transaction calculation computation is not happening inside the blockchain. It happens outside blockchain, and then something like only verifying the results of this computation happens on chain. So if you find this kind of difficult to understand, just feel free to interrupt me and don't hesitate to ask questions. So off-chain scaling solution do not need to modify Ethereum, so it can increase throughputs and speed as well. And then you can see off-chain means that you can inherit security and decentralization from Ethereum as well, because off-chain scaling solution stores some data on Ethereum. So Ethereum keeps those data safe. So we can, this scaling solution can inherit security and decentralization feature. So you will see this how state channel, plasma, rollup works. So state channel. Okay. Any questions? So state channel is, as I said before, it's kind of off-chain system. So state channel enables transactions between participants like A, B, off-chains computation while minimize interaction with Ethereum. So it's kind of a P2P system. But like when A and B wants to trade together, the problem is without this Ethereum, A and B should trust each other. But trusting is going for this Ethereum, and then A and B can trade kind of without worrying that something happens to their assets. So you can okay, so point is that A and B can trade as many times as they want. But Ethereum, they only store the result, initial and final states in Ethereum. That's the point. And then the process is like that. First of all, A and B should agree that they're gonna trade off-chain using a state channel, so they can deposit funds into this channel contract. Like, for example, A will deposit 10, B deposit 10. And then they also like assign those first deposit transactions. Then after that, they can trade. And then when they are done with trading together, first of all, they trade A, B, and then if they trade like when A transfer 1 ETH to B, the stake will be A11. And then they sign this stake as well. And then after they are done with this trading, they can post these final results to channel contract. So this channel contract it's only verified that two things. One is that total amount of money. So this channel contracts doesn't care how much they trade. They only check this 10 total amount is 20. So if they post the final transactions, final states with transitions, they can see that this 11 plus 9 is 20, so they can accept. And another one is that they see that these transitions is signed by both parties. They will not accept it. So those kind of things happens. So it's kind of simple, but there are some kind of attack vector for this system. Something like AB, it will start with A10, D10, then you will go like that. These channel contracts does not know which one is final one. So like these transactions, even though they are agreed with the third transactions, is A, B. A might submit this one to A's balance is greater than the third one. So A can post this one, and then channel contractor really gonna accept it because, as I said before, there are two conditions. They can verify these two conditions that total amount of money is the same as the initial amount, and then these conditions is signed by both. But actually, the final state is this one. So it can happen when B is kind of offline. So to resolve this kind of dispute, there are some kind of disputes time delay. That channel contract is gonna wait for specified amounts of time to for B can challenge with this another states that A just posted. So there should like usually 7 days is waiting. It's kind of a time delay for channel contract to finalize this state channels state. So yeah, that's happens. So set channel is kind of a goal is that off-chain transactions between participants with a minimal interaction with Ethereum. So minimal interaction is with Ethereum is important because Ethereum has limited resources in terms of this storage and computation. So state channel is, but state channel doesn't require Ethereum to verify every transaction's computation utility. So Ethereum doesn't care what kind of transactions happens between A and B. So it only care about these final transactions. That's why this time delay, this one. Time delay exists for state channel, and then that's why state channels wasn't chosen for scalability solution. It's kind of really hard, and then it also P2P system, so it's kind of difficult to scale, support many users, and also there's trust is required for these parties. So, and then another one is that Plasma. The concept of Plasma was proposed probably around in 2019. At the time, we thought that okay, scalability is done, scalability is solved, so we can happy with we will be happy with Ethereum with ultimate scalability, but apparently it's not. Plasma is kind of concept that it can optimize speed and cost by avoiding Ethereum from verifying all transactions. It's kind of a similar one. As off-chain is kind of off-chain solution is kind of make Ethereum not verify all transactions which happen on off-chain. But it's kind of different from state channel that there are no limitation to transactions between like how many parties can involve. As you can see, our state channel was 2, but Plasma was no. And then Plasma system, you can think of Plasma as kind of child chain working on Ethereum. So, but it's kind of similar. You can see, sorry. So it works like that. There are one operator for Plasma, and then it have this operator. It's got full control of computing every transactions in happening in Plasma system. So when user wants to join this Plasma system, this user should have to deposit some amount of money, and then operator keep looking at these contracts if there is any newcomer for Plasma, to this child chain, and then when user deposit funds in this Plasma contract, operator can verify this deposit transactions and then mint new assets for this user in Plasma chain. So, and then after this mints, a user can transact this off-chain using this inside this Plasma system. And then what Operator does is that he periodically stores the states of Plasma to Ethereum. That's how this Plasma system inherits security from Ethereum, because it stores Ethereum, it stores intermediate states into Plasma contracts, and then these states it's secured by this Ethereum. And then our user can trade, and then after user wants to withdraw their funds from this Plasma child chain, you can ask Plasma or Plasma contract that get back his funds. So Operator can, when Operator see these withdrawal transactions inside Plasma, it can process to say Plasma contract that hey, please give this user that assets that he deposited before, something like that. So, but you can see there are some kind of also attack vector. Yeah. So before okay, I will respond first. So in Plasma, there are some information stored on Plasma contract. One is that, as I said before, initial deposit, and state root means that this Plasma states it stored this Plasma contract, but not every transactions. Only state roots is stored this Plasma contract. You might how to manage states in the blockchain system. So it's only this information, root one, stored Plasma contract. Then Ethereum, they are responsible for securing this state roots, and then this Ethereum Plasma contract also resolve these disputes if this happens when the user and Plasma Operator have kind of a different view on these states of Plasma system. So in the case, there are a couple of attack vectors for this Plasma system. One is that probably you can find out, but this Operator is really centralized. So Operator is responsible for minting new assets when he finds out there are new deposit happens in this smart Plasma contract. But what if Operator stops working to mint or withdraw thing? So this one is really centralized. And then another one is that this Operator is the only one that knows what happens in this Plasma system. So if this Operator don't publish the new data that happens this Plasma, the child chain, no one knows what's going on inside the Plasma chain. So that's why mint and withdraw thing, it's gonna be a problem with this user, because this Operator doesn't process mint or withdraw transactions. This user's assets is stuck in this Plasma chain, so he will never get back his assets from this Plasma. So this kind of problem that happens. So and then after we found out that Plasma didn't solve this scalability solution, Rollup concept came out. Then okay. So before I said that the problem with this Plasma thing is that when operator doesn't publish the new data in happening is a Plasma chain. That's why the whole problem happens, because and then we call this problem as data availability problem. Data availability means that anyone can see. Okay. So Rollup is kind of the Plasma with the solution for this data availability problem. So Rollups verifies the results of calculation done is off-chain Rollup. And then it's kind of similar, but the only thing that the what makes Rollups different from this Plasma is that Rollups inside Ethereum. So there is also a Rollup operator. He is forced to publish data on Ethereum contracts, so anyone can see the new data that happens in this Rollup system, and then anyone can verify this data and then check out the final state is correctly calculated. So you don't need trust this central much output. Yeah. So probably the workflow is kind of similar, but this user needs to deposit funds this Rollup contracts, and then Rollup operator can mint new assets this Rollup chain, and then user can trade inside this Rollup chain as well. So, and then Rollup also periodically batched the transactions happening in this Rollup chain, and then storing only results and data to Rollups, to Rollup contracts on Ethereum. So the role of Ethereum for Rollup system is that Ethereum verifies this result correctness, and then finalize these conditions as well. So and probably think so. Rollup means that you can imagine from the name of this Rollup that many transactions happening on Rollup system. We usually call it layer 2 or layer 3, but we can roll these transactions into one, and this one transactions will go with Ethereum. As you can see that one transactions for Ethereum are going to take care of these all transactions happening in Rollups. So transaction fee in Rollup system. It's much lower than transitions for Ethereum itself, because only one transaction needs to be paid with multiple transitions. So state change is kind of change in the user's account states in Rollup, and usually probably up. So another one is that we need to prove this calculation integrity, which means that inside Rollup there are multiple transitions. Rollup operator process these all transitions. It builds another new states. So previous state is S, and then there are batch of transitions happens, and then there are new states. So Rollup operator needs to prove the new states correctly. So anyone and any users in the Rollup system can trust this Rollup operator, and then if this new state is calculated correctly, the users can stay. And then there are two ways of proving this computation integrity. That's how we optimistic rollup and zk-rollup. So I think I can cover this one. So I will explain this optimistic rollup first. So as I said before, in rollup system, there should be this rollup system one prove this computation integrity. Another one is that this rollup operator should publish the data. So this anyone can verify this computation integrity with this data. These two things is really important. But Ethereum is kind of really expensive for computation thing. So with optimistic rollup, this verifying computation integrity doesn't happen on chain. It's gonna rely on off-chain system called third-party verifier. So optimistic rollup only stores data on Ethereum, and then these optimistic rollups, it's kind of rely on third party to verify this computational integrity. So that's why optimistic rollup has kind of as you see that in the state channel there's a disputes time delay. Anyone can challenge if they can notice that some states published on Ethereum is kind of different than they are actually calculated. So optimistic rollup has kind of also has some similar concept, this time delay. So when optimistic rollups periodically post their final states on Ethereum, it's not directly finalized. Ethereum is going to wait 7 days to finalize its the states that's submitted from this optimistic rollup. So that's why because Ethereum are waiting for third parties to verify these final states and data to be verified, so that optimistic rollup just posted. So that's how, but there is reason why optimistic rollup chose to work like that. As I said before, computation on Ethereum is really expensive and limited. So it's kind of trade-off that you can pay more, you can process this verification computation on Ethereum, but optimistic rollup is designed to delegate this verification process to a third party, and then trade-off with this approach is kind of some kind of delay.
Yeah. How can the outside work? So they need to reach the 4 states.
Yeah.
They on state on 30. So it takes a lot of time because they, does it take a lot of
Actually, no, because this third party keeps storing the data published on it from optimistic rollup every time. So this third party keep those data, and then every time a new data comes from this optimistic rollup, then they can verify with this new data with the. So
why should we wait for 7 days for that?
Yeah. There's no like a. I don't know why they came up with the 7 days, but they think 7 days is kind of third party can challenge with this final states. So there's actually no reason, but we can like make it shorter. When user A wants to withdraw their money from optimistic rollup, they can use third party to make this withdrawal process faster, because third party knows its final states when they verify these new states by themselves. So they can, this third party actually borrows money to users, and then this third party can make a profit from this borrowing, because A is gonna pay them some kind of service fee for fast withdrawal. So those kind of things that rollup users for rollup, optimistic rollup usually do, because third party keep those all data that happens that's been happening on optimistic rollup, so they can make sure that they are sure that this new states is correct without waiting for 7 days. So that's why third party can give them money without worrying about any misbehavior from optimistic rollups.
There is a test.
Yeah. Yep. And then this, yeah, third party gonna take all risk, but user A can get money faster than 7 days waiting. So it's kind of things. So we need to prove that this computation integrity. So optimistic rollup is kind of rely on third party to prove this integrity, but that's when zk comes in. zk can prove that this computation is done correctly with using cryptography and so that I don't actually fully understand about that. Anyway, so I think we are gonna take a 5 minutes break because I'm gonna explain zero knowledge and zk, of the modular blockchain stuff. It's kind of hard to digest at first. So yeah, 5 minutes break. I don't get to zoom down. Okay, zoom down. 네, 안녕히 계셨습니다. 정신은. But I have some friends in different party. 아니야, 뭐 드셔. 하려고? 아, 네. 뭐 여쭤보시던데 이런 빨리 보니까 네트워크 딜레이 관련해서 레이턴시가 관련해서 리서치에서 있긴 질문 있어요? 저 여쭤보고 싶어요. 선생님과 후배 레이아웃에 있긴 있을 거예요. 저한테 다른 연락이 there are global people who are working on this agency, but they are working for privacy and scaling team. So, yeah. 제가 한번 나갔다 들어. 아니요. 아이라테까지 아닙니다. 빨리 넘어가야지. I'll start. So, zero knowledge tech is used for two reasons. One is that privacy, and another one is that scaling. But what you can do with zk is that you can prove this computation integrity. So those two, privacy and scaling, can be achieved because zk can do this computation integrity. So let's find out what zk proof is. Before zkp, we can what's proof? Proof is kind of a fact or piece of information that shows something exists or is true. So you can see this kind of pieces that's proof that, and then this theorem might be we can call it statements that states that something is true, or and then to support these statements, that there is proof that why this statement is true. In computer science, probably you might hear about this graph isomorphism. That isomorphism is kind of the structure preserving mapping between these two structures of the same type. It looks like a different graph, but you can check out this vertex and edge. They can have same structure. it's kind of really hard to find this permutation to satisfy this isomorphism. But if you know answer for this isomorphism, it's really easy to verify. You can see that these two graphs is kind of same structure. So we call it NP problem. You might be familiar with. So NP is kind of problem that is really hard to solve, but it's really easy to verify the solution. So usually zk thing is kind of to solve this kind of NP problem, something like that. Yeah, so if you know, you know the answer, but you are not gonna tell this answer to anyone, but you can say that you know the answer, but I'm not gonna tell the answer. But how to prove that you know the answer? Every time anyway, so there are two entities. One is the prover, another is the verifier. Prover is the one who with answer or solution. Verifier is the one who verified that the statements from this prover. So I'm gonna take this tricolor graph. This tricolor example that is this graph. It's consists of three. There's some conditions. One is that three. This graph consists of three colors. Another one is that what is connecting each other is have a different colors, like red, blue, purple, like that. It's kind of a solution. So prover is gonna prove that he has the tricolor based graph, but not gonna tell the graph. But he want to prove that he know the answer. So you can prove interactively verify can choose a random number, that this number might ask prover that any random two vertex and edge, and then the prover choose this one and then respond to this information. It's random one, and then this correct, which means that okay, there's three two colors in this answer, and then in the answer this vertex has different colors, and then they can then verifier can believe that this prover has answer, and then verifier can ask again, and the prover returns, and we can keep going. And then the more questions verifier can ask the prover, and prover responds with a correct answer, verifier can the more the verifier can push make sure that our prover knows the answer. So this kind of process, so we can call it interactive proof, because verifier and prover interacts. But can see that if verifier ask prover 100 times, there is some possibility that prover doesn't know the answer is that 101, right there. But the problem with this interactive proof is that there are a lot of communication first, and then the communication cost is quite high. So, so we need to reduce the size of this communication and then proof size. Sure. So that's when snark and stuck things came up. Probably this one is the last slide about the zk. And then if you want to know about the details of zk, probably just ask me. I can send you some materials. But I just want to say one thing, that the snark is kind of stands for succinct. Succinct means it's small. N is non-interactive. And the argument of knowledge is, but we don't care about that. But snark and stuck is kind of things that they are kind of scheme to reduce the size of proof, and then make this whole process effective. So and then yeah, those kind of things that zk can do. So probably you can understand zk more with the examples of zk-rollup. So let's find out what the zk-rollup does. Before we are talking about the optimistic rollup, I say that a third party usually verifies this computation integrity, but you can remove this third party and we can replace this third party with a zk. So we don't, in zk-rollup, we don't need to trust anyone. We only trust this mathematics. Okay, and then this zk-rollup use this zk to prove that the older states S, and then there are many transitions happening in zk-rollup, and then after calculating these transitions with the older transitions, there is a new transitions. So the correctness of calculating these new states can be proved with the zk, which means that you can you need to make some kind of some logic to turn these state transitions into zk. It's kind of really difficult to do. So that's why actually optimistic rollup, it's kind of optimistic rollup came out first, because you don't need to make any difficult software for this optimistic rollup. But zk thing is you need a specified software to make this zk proof for this computational integrity. So and then in zk-rollup compared to optimistic rollup, this rollup contract on Ethereum is different. On optimistic rollup, this rollup contract's role is only to store data published from optimistic rollup, but zk-rollup, it needs to rollup contracts also verify this zk proof generated from this zk-rollup. So there is no need for time delay for challenging periods that have exist in the optimistic rollup. So there's no time delay. Finality is given after verifying zk proof on rollup contract. So zk-rollup has fast finality. So that's another advantage that zk-rollup has. But the problem, some kind of problem is that, as I said before, computation on Ethereum is kind of expensive. So transaction fee on zk-rollup is kind of higher than this optimistic rollup. But if you want instant finality, you need to use zk-rollups. Actually, zk tech was kind of impractical to become products level a few years ago, but like around 2019 or 2020, there was a breakthrough that actually to make this zk's tech practical to be applied for this kind of old system. So that's why recently you can see many zk projects, including zk EVM. You might heard of it, but can explain later. Yeah. Anyway, in zk system, we use zk to prove that these many conditions that should be satisfied and this rollups, like sender accounts, receiver accounts. Also, this signature is correct. Correctness also should be verified on this zk. So this kind of summary that some scaling solution that has been happening in Ethereum ecosystem. So at this moment, this zk-rollup is kind of the ultimate solution for scaling on Ethereum. But yeah. And then any questions about solving?
Well, what if upgrade to
There is some kind of commitment scheme called AGG. It's kind of really make commitments for this all zk thing much more effectively than anyone. So this new commitment scheme is kind of brought a breakthrough in zk space. So recently many zk scheme came up, but they kind of all are based on this. We call it cartel commitments. Yeah, cartel commitments. It's a really efficient way to make commitments on any data. So and then probably another I will try to explain that. Okay. Let's suppose that there is some computation that you want to prove. The first thing that you need to do is that you need to turn this computation into arithmetization. So you can prove that this whole process inside this computation is correctly done. So it's kind of a math thing, but and then usually polynomial is used to describe this arithmetization, and then you can prove this polynomial. You can you can say that you have the answer for this polynomials. And then, but this polynomial is really big to support this any general computation. So the important thing is that how to prove that this polynomial thing to of data. So that's when commitment schemes came up. So you need to generate this commitments based on this big polynomial to verify it. And then this size of commitments was kind of is needed to be really small to make this verifier to verify this computational integrity with a small amount of data. So in actually this cartel commitment came up around 2020. Then at the time, verifier actually do verification in polynomial times, even though this computation thing is really big. That's kind of breakthrough. And then there are a couple of things also we can describe as breakthrough, but I think this one is kind of main one. Make it practical. Yeah. It's gonna be this kind of raised of the block space. Roll back to the state before the assemblies. Not yet. Yeah. But theoretically, because the existing optimistic rollup, like optimism or arbitrum, is run by only one single sequencer. So, and then they do not want to do any harmful behavior to their network because they have the whole responsible for those networks. So that's why there's no any challenging thing happens. But right now there are these optimistic rollup and arbitrum are planning to decentralize these sequences because the centralized sequencer have many problems. But at the time, we can see any bad thing happening on their network if there are some sequences to so let's find out what Ethereum is gonna do with this rollup. We probably already 3 years ago he brought this Rollup-centric Ethereum because at the time rollup is kind of they chose this rollup as a ultimate solution for scalability. But there are monolithic blockchain thing, which means that it performs all operations of blockchain on single blockchain, like a Ethereum, Solana, Binance system. There only one they store data and then executes transactions, and then and then also publish the data. Everything happens on one single blockchain. That's why we still stuck with this trailer mapping. And then Rollup-centric Ethereum, we can do much better than this one. I mean, I will explain this. But I think you are kind of familiar with this modularization thing. And then we can break down this task of blockchain into individual modules. You might you can check out this blockchain process first. It's kind of simple. So user can send transitions to mempool, and then miner or sequencer for layer 2 example. They choose what kind of transitions is gonna be included in next block. And then miner verifies these selected transitions are valid, and then miner can create a block, and then this propagates to other miners to verify this block, and then this block can be finalized as the next block. That kind of a basic one happening in blockchain space. But we can divide this task one into execution and settlement, we call it. So execution means you can think of here Rollup as kind of execution layer. That this execution layer only are responsible for executing transactions, and then calculate the next states, and then next states is verified in this settlement layer. So settlement layer is kind of the one who provides a security to this execution layer. And then in settlement layer, we don't need to execute every transactions. Settlement layer only verifies the final states of from this execution layer. So execution layer is do every process thing for next block. So we can divide one blockchain into two, execution and settlement. Rollup as a layer 2. And then settlement layer is kind of layer 1, Ethereum. It's kind of typical one, but we can go further. As I said before, storing data on Ethereum is really expensive. That's why we came up with some kind of data availability layer. So we still depends on Ethereum as a settlement layer to verify this execution. If to check out this execution is done correctly, but data is not needed to be stored on Ethereum. We can depend on another layer called data availability layer. And then when settlement layer verify this the results of execution layer, this settlement layer can fetch data from this data availability layer, and then it can verify those things. The reason why we are doing this is that we can make transaction fee much more cheap because data is stored not on Ethereum, which is really expensive, but then another layer only can take care of storing data for Ethereum. So there are a couple of projects are doing this. Another one is Polygon D. I forgot the name of Polygon DA or something. Then they have their own committee to make this data availability layer secure. So the cost to store data is they're gonna keep those costs really cheap, much cheaper than this Ethereum. So we can process transactions with a very low transaction fee because data availability layer can provide a low fee for storing data. And then it's kind of a decentralized storage, but they do not care about what kind of data to be stored. They do not verify this data is valid or anything. They just store it if the user pay fee for storing. Yeah. Then the validity of data is checked on settlement layer, not data availability layer. That's why they can keep those costs kind of low because computation is not needed for data availability layer. So it's kind of a work division, settlements, data availability to, and then data availability to store data, the execution in something like that. And then another concept recently came up, which is sequential layer, which is that actually my project is doing at this moment. Sequential layer is only confirm the order of transactions. This sequential layer doesn't execute transactions. They only construct the block and then deliver this block to execution layer, and the execution layer just execute the transactions inside this block, and then settlement layer to also verify this stuff. The reason why sequencing thing is getting hype these days, because I will explain later. So modular blockchain ecosystem like that, as I said before, there's a data availability, and then user submit transactions to sequencing layer, and the sequencing layer make a block, and then block is executed in Rollup. Rollup is as an execution layer, and then the result of this execution to be posted on Ethereum as a settlement layer, and then the settlement layer verifies this the final states, and then when this block is posted on Ethereum, and then this finality is given for this data. And then yep. That's really good questions. It can have consensus mechanism or not. Yeah, it's a kind of choice, because so sequencing layer, as I said before, only creates a batch of transactions for block, so they can confirm this order of transactions. So only one single sequencer can confirm this order, or you can have a multiple sequencers, and then they reach consensus every time when they build a block. The reason why you might think that consensus is needed because these something bad can happen to this block, and then if this sequencing layer is kind of centralized, this sequencing layer can have invalid transactions in a block, or prevents a bad thing happening in the sequencing layer. But yeah, usually you can, when building a block. Actually, I think it's time I need to mention about this MEV stuff, because MEV is kind of it's all about this ordering transitions in a block. So there is good MEV, which is like a arbitrage or liquidation thing, but there's also bad MEV, which is front running and sandwich attack. So it works like this. And you can create conditions to swap to DAI to E. But before this transition is confirmed in a block, miners or sequencers can see your transactions, and then they can think that the price of Ethereum is going up because you are going to buy this ETH. So, so these miners or sequencers or MEV bots can put some transactions in front of your transactions before processing your transactions. They can buy Ethereum first, and then later they can sell Ethereum. So they can make a profit, because and then you will be ended up with buying Ethereum with higher price, which means that financial losses on your side. So this is kind of a sandwich attack happening when the power to order or censor transactions in a block belongs to any centralized entities. So that's actually what's happening in this Rollup ecosystem at this moment. Because as I said before, Rollup's ultimate goal is to provide a maximum scalability. So they usually keep only one single sequencer, but this only one single sequencer can do anything they want to do. So they just put like this kind of attack to users. So to prevent these kind of things, you can think of like a consensus. So you can keep your eyes each other. Yeah. So and yeah. So that's why these existing rollups like Stackware or Polygon, Scroll, they have their own strategy to decentralize these centralized sequences, because these kind of bad things can happen on the network, but they don't want to let them happen on the network. So
What is a blockchain? It's good for scalability, I think, but like speed. Is it speed? The transaction processing speed is better than administrative blockchain because when I send a transaction to modular blockchain, many different parts to be processed.
yeah, you're correct. Latency might be gonna be problem. So that's why these Rollup projects came up with some kind of soft commitments. There are
Guarantee finally.
yes. Finality will be given when these your transactions be included in Ethereum. But before that, we can guarantee that your transaction is fine with us. But like that's why we call it soft commitment, which means that layer 1, layer 2, and then a user when submits transactions, and layer 2, let's suppose it works with a consensus model, and then with layer 2's own consensus model, we can provide this layer 2's finality to users. But it's not finalized on layer 1, which is provides a settlement layer for this layer 2. That's why we call it like a soft and then sometimes pre-finality or confirmation. So that's how these layer 2 projects some kind of to make this user experience better with some kind of low latency, but ultimately latency will be some problem. But we can guarantee that we can force this layer 2 projects, layer 2 protocol to not any harmful behavior to users. Like after when user find out that this layer 2 is sequencers do a bad thing to them, then they can claim layer 1, then these sequencers for layer 2 can be slashed. Those kind of things, because the soft commitment will be signed by sequencers in layer 2, and then the user can prove that he can get some kind of soft commitment signed by layer 2 sequencers, and the layer 1 can check out that layer 2 also actually promised to users that these users transactions will be included, but if it's not, they can penalize these sequences. Those kind of things can happen. So latency might be a problem, but there are some research to feel those to make the users feel that there's no latency. So Um, yeah, because before pivoting to building sequential layer, our project actually built layer 3 on Starknet. So but we think and then I know some projects that actually building a their zk-rollup on Starknet as a layer 3, because Starknet project Starkware provides their own scalability engine called the StarkX. And then if you use this StarkX, you can build layer 3 quite easily. The layer 3 is usually app specific rollup. So if you want to build you want really maximal scalability and then really low transition fee, layer 3 is kind of option for you to choose to build your network. So there are DEX or perpetual exchange projects actually building layer 3 on Starknet, and then the existing probably almost all layer 2 projects are really interested in building layer 3 ecosystem top of them, and then like optimism, forgot the name, but yeah, and then zk-sync, and then Scroll also has their own strategy to build a layer 3 ecosystem. So, but I don't think that like optimistic rollup or any kind of EVM compatible rollup is kind of okay with layer 3. I mean, I don't think. I think that zk-rollup is only kind of a perfect match for a layer 3. The reason why I did optimistic rollup is kind of, as I said, a time delay is needed for finality, and then EVM is kind of it's too heavy to become layer 3, because the reason is that layer 3, layer 2 is usually got inherited security from Ethereum. The reason why they can inherit security from Ethereum, they post data to Ethereum. That's why this security, why this rollup project can security from Ethereum. But there is some limits that they can get advantage from this post this data to Ethereum. So that's why usually app specific rollup it's good for layer 3, but not like the EVM or optimistic rollup is. So yeah. Yep. And then another one is that I mean, I become kind of shy that I'm going to explain what my project is doing. So sequencing layer usually gonna have multiple a variety of rollups is gonna share on one single sequencer, because as I said, rollup network usually have really low transition fee, which means that with only transaction fee, rollups is gonna be really difficult to make this network sustainable, because this transaction fee is kind of revenue model for these rollups. But if this transaction fee become low, this rollup, there is no profit or no revenue for these rollups, because they also this rollup project also needs some money to run sequencers and process the transactions from users. So this economic thing is really important. So that's why MEV is kind of really getting hype in this rollup space, because using this MEV, rollup can make their network sustainable, because they can make a profit from this MEV stuff. So and then to maximize profit from this MEV stuff, there's cross rollup MEV also exists, which means that there are a couple of rollups, and then you can also make profit from only one rollup, but there are some opportunity to generate additional profit from this cross rollup MEV when you can make like an Ethereum to DAI on rollup 1, and then on rollup B, DAI to like a Binance, and on rollup C, Binance to ETH. If you can process these all three transactions synchronously in this system, end up making profit from these transactions. So this kind of opportunity can happen because rollup is gonna be like many projects are thinking of making their own network as rollup, because rollup usually give them flexibility, scalability compared to a smart contract. To make it so to support this cross rollup MEV stuff, we need to share a sequence layer, so this sequence layer can take full control of making this transition inside blocks that will be provided to these rollups. So that's why it's kind of centralized. And then there are a couple of things that actually our project is doing, but you can read some articles about projects, so I don't need to explain all of this. But only one thing that I want to emphasize, that as some students actually ask, that if you want to prevent bad thing happening from these rollups, you can apply consensus. To make a block. But in our projects, we use cryptography scheme with encryption and zk to prevent this bad MEV happening on the network. So basically, using this encryption and zk, we encrypt transactions, so this sequencer cannot check out the contents of that. So that's then they cannot manipulate the order of transactions, because this contents of transaction is hidden from this sequencer. So front running or sandwich attack can be protected on user side. So these transitions is encrypted. So we can only have one single sequencer to build a block, and then we can mitigate the centralization issue with this encryption. And then, but the problem is that some malicious users can attack this sequences with invalidated encrypted transitions. So that's why we applied zk to prove that this encrypted transitions is valid without decrypting. So this operator can make sure that this encrypted transition is valid without decrypting it. So that's how to prevent waste of this block space and computing resources. So we don't need in our system, we don't need a consensus. Consensus usually we use cryptography scheme to remove this consensus process, because we think that this consensus process is kind of sacrifice scalability for rollups. So that's what our project's different. What make our project different from any other projects. So actually, we published our cryptography scheme called PVDE. It's a practical verifiable delay encryption. And then we applied this our own cryptography scheme to build our own sequencing layer. So if some Rollup projects interacts with our sequencing layer, we can make sure that there's no sandwich attack inside a block that we can provide to Rollups, and then Rollup can trust us, and then they just only execute those conditions, and then users for these Rollups are not gonna attacked by this NAD stuff. So that's what we. Yep. That's a secret. But yeah, that's why we call our cryptography scheme called practical. As you said before, we need to prove that this encryption process is done correctly with zk, but it's kind of too heavy to run to generate zk proof for this encryption. But we did it. We use our another scheme. We combined Sigma protocol and zk snark to make efficiently. We can't say the details, but anyway. Yeah. Yeah. Right now, it takes 3 or 4 seconds in browser to generate this GKP, but it's an initial implementation, so we are actually optimizing it for better performance. So our target performance would be 1 or 2 seconds when you generate like short transitions for X. We use zk snarks, so proof size is constant. So I forgot the exact size of that, but it's not that big. Probably, yeah. You know, every zk snark scheme will similar the size of the proofs. key, you mean the scheme from Polygon, or there's a Pong? Okay. Our initial implementation is actually based on Pong. The Pong key. Pong key is, I think, another kind of optimized scheme developed by Polygon. And then there's a Plonky and Plonky 2, those kind of things, but we haven't applied those things to will. Yeah, but current it's based on Plonk. Okay, so thumbs up. Yep.
Different rollup methods and the project or rollup different template. They have
Yep.
Okay, then I don't understand how the different they different rollup probably use their same.
I mentioned synchronous. It doesn't like execute at the same time, but we can make sure that these transactions related to cross rollup MEV is going to be included in next blocks for each rollups. And then, even though these rollups process in different time, we can make sure that these transitions gonna be processed in the next block. That's why I mean it's synchronous, not like at the same time. Not as soon as possible. It's I would say next block. Yeah. They can make a much they can make additional profit in this cross rollup. Yeah. Point is that these profits made from this good cross rollup MEV is going to be no users. I mean, you just can yeah, not users. Yeah, those profits are gonna belong to rollups or sequences, but not rollups because this MEV stuff is one of the revenue model for rollups. So to users as well, but it's a choice of how to design this whole rollup ecosystem, because I just MEV is kind of a good revenue source for these rollups. So if you want, if some project wants to give some incentives to users, they can distribute it to users as well. But at this time, rollups operator also needs some kind of revenue to run this that run their networks. So yeah, that's just choice of them. Yeah. So thumbs up. Last one is that is this conference happening in June. I'm kind of a mentor for ETH Soul, and then kind of a community partner for Bit-Relation. So they want me to say that this conference is happening. So thank you. Thanks so much.